ladies and gentlemen. My name is Kisi Joshua, and I'm honored to be here with my team to discuss some concepts of the computer memory hierarchy. These concepts in this presentation are the associative memory, the cache memory, and then the bank memory. But before we move any deeper into diving or talking about these concepts, I would love us to talk about what a computer memory is. So what is a computer memory? A computer memory is like the brain of the computer that enables the computer to store information, whether temporarily or permanently, that can be accessed in the future. We have three types of the computer memory. That is the primary storage memory, the secondary storage memory, and then finally the tertiary storage memory. So what is the primary storage memory? The primary storage memory is the RAM of the computer. That is the random access memory that helps store information temporarily to be used by the user in the short term. We have the secondary storage memory, which is the permanent storage memory of the computer that stores information for a longer period of time permanently. And then finally, the tertiary storage memory that archives data that the user will be needing not on regular basis. Now, let's imagine our digital world to be like a grand library. Traditionally, before any book is accessed, the librarian will have to look for the book. But with associative memory, it is as if the librarian has a certain superpower to access this book based on its contents. Great superpower, but with some limitation and complexity. Moving forward, let's envision a mansion with many rooms and great treasures. Accessing these rooms will take time if being accessed step by step. But with the bank memory, it divides this mansion into wings of rooms that can be accessed simultaneously. Now finally, we have the cache memory, which we can consider a chef's perfectly organized kitchen where ingredients can be accessed within arm's of reach. So the cache memory mirrors this efficiency by placing data or information close to the CPU that can be accessed easily by the CPU. So did you know this concept forms the backbone of the technologies that we use today? With curiosity as a guide, I would love us to dive deeper into these topics. Thank you.
Hey everyone, my name is Mark. Today I want to talk to you about associative memory. So what exactly is associative memory? Well, it's a type of computer memory that allows for fast and efficient data retrieval. In simple terms, associative memory works by associating data with specific tags. When we want to retrieve information, associative memory uses these tags instead of searching through the entire memory to quickly locate the desired data. It makes it incredibly useful for tasks that require fast access to data in memory. There are various types of associative memory, such as the content addressable memory, which is the CAM or the CAM, and the associative cache. The CAM is particularly interesting because it allows us to search for data based on its content rather than its address. This makes it ideal for applications like pattern recognition and database systems. Now for the associative cache. These are a type of cache memory that allows data to be stored and retrieved based on its content rather than its specific location. This means that the data can be accessed quickly as cache can search for the desired data in parallel. It's like having a smart memory that can quickly find what you are looking for. Now, let's talk about the advantages of associative memory. One major benefit is its speed. Since associative memory can retrieve data in parallel, it significantly reduces the time it takes to access information. Additionally, it enables efficient caching, which helps improve overall system performance. Associative memory finds its application in various fields. For example, associative memory is used in network routing to quickly match incoming packets with their appropriate destination. It's also widely used in database systems, allowing for efficient data searching and retrieval. To sum up, associative memory is an essential component of modern computing. Its ability to quickly retrieve data and improve system performance makes it valuable assets in the various applications. Thank you for your time.
Guys, so my name is Owusulos Nanejibia, and we'll now be looking at bank memory. What is a memory bank? A memory bank is a logical storage within computer memory that is used for storing and retrieving frequently used data. A bank consists of multiple rows and columns of storage units, and usually spread out across several chips. In simple terms, banking can be defined as placing chips in a number of rows and columns at a given level of a memory hierarchy. In a bank memory system, the data is divided or interleaved across the memories so that each memory contains only a fraction of the total data package. Now let's look at the history of bank memory. Banking of memory was introduced in the 1980s and in the early 1990s. It allowed computers with limited address ranges to access more memory with a linear scale. Computers that were invented in the 80s and the 90s faced challenges in accommodating large amounts of data. Hence, the bank memory system was developed and came up with the idea of dividing memory into segmented banks, which made accessing data much easier. Moving on, we'll now look at the different types of bank memory. Bank memory comes in different forms, each designed to address specific hardware and software needs. Some types of bank memory include the segmented memory, which divides the address space into segments, each with its own memory bank. Another type of bank memory is the bank switching, which involves the multiple banks of memory, usually of the same size, which can be swapped in and out of the CPU's addressable range. This technique was used in systems with limited address space to overcome memory constraints. Now on to the functions of bank memory. The primary function of bank memory is to expand the accessible memory beyond the processor's addressing capabilities. It goes about this by allowing the processor to switch between memory banks. Computers could effectively access different portions of memory. In a system with a bank memory, the available memory is divided into segments. Each bank is a distinct portion of a memory, and the system has the ability to switch between these banks. This technique is particularly useful in applications that require more memory than the hardware's address space allows. By dividing the memory into banks and allowing the CPU to switch between them, bank memory provides the illusion of a larger memory space. Despite the benefits it holds, bank memory is less common in modern computer architectures as compared to earlier systems due to the increase in addressable memory space provided by 32-bit, 64-bit, and higher processors. However, the concept of segmentation and management units in modern systems can be seen as a distant relative of bank memory. Some examples of systems employing bank memory are the embedded system and in the legacy systems. Also, bank memory contributes to multitasking. In systems with bank memory, different memory banks can be allocated to different tasks. This separation allows the CPU to switch between banks while handling various tasks, improving multitasking capability purposes. In summary, bank memory is a solution to address space limitations by dividing memory into banks and allowing the CPU to access different banks of data at different times. This technique expands the usable memory for applications that require more memory than the hardware's native address space can accommodate. This concludes my presentation on bank memory. Thank you for listening.
Guys, so my name is Christian and I'll be taking you through a look on cache memory. What is cache memory? Cache memory is sometimes called CPU memory because it's integrated directly into the CPU chip or placed on a separate chip that has a separate bus interconnected with the CPU. Because it's physically closer to the processor, it provides a faster path for data access. In order to be closer to the processor, cache memory is smaller and is more expensive than the main memory but uses a higher performance. What it sacrifices in size and price, it makes up for in speed. Cache memory operates between 10 to 100 times faster than the RAM, requiring only a few nanoseconds to respond to a CPU request. The hardware that is used for cache memory is the high-speed static random access memory, SRAM, and that used in a computer's main memory is the dynamic random access memory, the DRAM. Now to discuss the various types of cache memory. It is categorized as levels that describe its closeness and accessibility to the microprocessor. There are 3 general cache levels, the first being the L1 cache or level 1 cache. This is sometimes called the primary cache, and is extremely fast but relatively small and is usually embedded in the processor chip as CPU cache, providing the fastest pathway to data access. Then there is a level 2 cache or L2 cache. This secondary cache has a higher memory capacity than the L1 cache. L2 may be embedded on the CPU, or it can have a separate chip or coprocessor and have a high-speed alternative system bus connecting the cache to the CPU. That way, it doesn't get slowed by traffic on the main system bus. Then finally, there's a level 3 cache, L3 cache. This is a specialized memory developed to improve the performance of L1 and L2. L1 or L2 can be significantly faster than L3, though L3 is usually double the speed of the DRAM, which is the main RAM of the computer. With multi-core processors, each core can have a dedicated L1 and L2 cache, but they can share an L3 cache. We shall now dive into cache memory mapping. Caching configuration continues to evolve, but the cache memory traditionally works under 3 different configurations. 1. The direct map cache. This has each block or data mapped to exactly one cache memory location. Conceptually, a direct map cache is like rows in a table with 3 columns. A cache block that contains the actual data fetched and stored, a tag with all or part of the address of the data that was fetched, and a flag bit that shows the presence in a row entry of a valid bit of data. The second is the fully associative cache mapping. This is similar to direct mapping in structure, but allows a memory block to be mapped to any cache location rather than to a pre-specified cache memory location, as is the case with direct mapping. Lastly, we have the set associative cache mapping, which can be viewed as a compromise between the direct mapping and the fully associative mapping, in which each block is mapped to a subset of cache locations. Finally, let's take a look at the locality principle cache memory operates on. The ability of cache memory to improve a computer's performance relies on the concept of locality of reference. Locality describes various situations that make a system more predictable. Cache memory takes advantage of these situations to create a pattern of memory access that it can rely upon. There are several types of locality. 2 key ones for cache are temporal locality. This is when the same resources are accessed repeatedly in a short amount of time. Then we have the spatial locality, and this refers to accessing various data or resources that are near each other. With that, we have reached the end of this walkthrough on cache memory. Thank you for your time.
Guys, so my name is Donald Jackson, and I'm going to be wrapping up everything we've looked at in this video tutorial on memory. So, we took a look at memory in computers and saw that they are the storage mediums of computers and can be divided into the temporary storage like the RAM and the permanent storage like the hard disk drive. We also saw the fact that the computer's main memory, contrary to general knowledge, is actually the random access memory, that is the RAM. Then saw that the RAM can be segregated into the SRAM, which is the static RAM, and the DRAM, which is the dynamic RAM, with the former retaining its memory content as long as power is supplied to it, whilst the latter's memory content has to be continuously refreshed. We then moved on to look at bank memory and identified that bank memory, also known as memory banking or memory segmentation, refers to a memory management technique used in computer systems to efficiently organize and access large amounts of memory. The purpose of bank memory is to overcome limitations in addressing capacity and memory access speed. In bank memory systems, the memory address space is divided into multiple segments or banks, each with its own address range. Each bank can be accessed independently of the others, allowing for parallel access and increased memory bandwidth. This is particularly beneficial in situations where a single memory bus or address path may become a bottleneck when multiple components, such as processors or peripherals, need to access memory simultaneously. We also looked at associative memory and said that it's a type of memory or data organization where information is retrieved based on its content rather than its specific location or address. Associative structures are designed to provide fast and efficient lookup operations, allowing for quick retrieval of data without requiring knowledge of its exact storage location. We take a keen look on some key types of associative structures. Content addressable memory, or CAM. In associative memory, data is stored with associated tags or keywords. When a search is performed using a particular tag, the memory system returns the data associated with that tag. It's as if you're asking the memory, do you have any data with this tag, rather than providing an exact memory address. Another associative data structure is the associative array, which is a data structure that maps keys to values. It allows you to store and retrieve values based on their corresponding keys. It allows you to associate a value or data with a unique key, enabling efficient retrieval and storage of information. Finally, the content-based retrieval in databases and information retrieval systems can refer to techniques that retrieve data based on its content rather than traditional search methods. For example, searching for documents based on keywords, phrases, or similarity to a given document, and can be considered in associative retrieval. We finally take a look on cache memory, which is the fastest among the temporary memories. Cache memory is a high-speed, small-sized, volatile computer memory designed to store frequently accessed data and instructions in order to provide faster access to the CPU. It acts as a buffer between the CPU and the slower main memory, helping to reduce the latency of memory accesses and improving overall system performance. Cache memory is organized in different levels, that is L1, L2, and sometimes L3 caches, where the L stands for level. These levels represent different layers of caching, each with varying sizes and proximity to the CPU. And the L1 cache is the closest and fastest cache to the CPU cores. It is sometimes embedded into the CPU core or placed right beside it, which makes data retrieval very easy and efficient. L1 cache has the lowest latency, but is also the smallest in size. The L2 cache is larger than L1 cache and sits between the L1 cache and the main memory. It is shared among all the cores on a multi-core processor. While it has higher latency compared to L1, it still provides faster access than the main memory. Now, some CPUs have additional level of cache known as L3, which is larger than L2 and shared among all the cores on the processor. It serves as a shared cache and is further away from the CPU cores compared to L1 and L2 caches. So, that is all we have for you today on computer memory. We hope you enjoyed the video.